Good morning, everybody. Good morning. My name is Ron Ashburn. I'm Executive Director of the Association for Iron and Steel Technology. It's my honor to welcome you to AISTech and to our Brimacombe Memorial Lecture. It's a new venue for us this year, but you all passed the first test, which was orienteering yourselves to the Brimacombe Memorial Lecture. So congratulations. Give yourself a big round of applause for getting it right. Thank you. All right, before we begin, I do want to point out our emergency egress route. So if we have to evacuate this room, you go right out the doors you came in, turn left, and go out to the street. It's right there. That's our route. And although this is our opening session, we actually kicked off the conference yesterday with the AIST Foundation Golf Classic. Our gratitude to all the golfers that went out. They helped raise over $30,000 for our scholarship and grant program associated with the AIST Foundation. So kudos to all of our golfers. Absolutely. Thank you. And starting this morning, this year's conference, I'd like to point out there's 475 technical presentations. This is number one right here. So we're just getting started. We have over 1,600 authors from about 35 different countries. It's truly a global event, and I'm also pleased to note that we have an excess of, we're just about near 8,000 people for the overall event. So it's going to be one of our biggest, if not the biggest of all time for AISTech's history. And this year, we want to thank all those that are here this morning and representing the first time, indeed, that AISTech will be in Columbus, Ohio here. Now, tomorrow morning at 8 a.m. will be the President's Award Breakfast. We'll be featuring our keynote speaker. The Hogan Memorial Lecture is Maximo Bedoya. He is the CEO at Ternium. Now, that event is sold out at the ballroom capacity, about 1,300 people, so I hope some of you are already signed up for that, and we'll see you there tomorrow morning. And then on Wednesday morning, our third plenary session, that'll take place at 10 a.m. So 8 a.m. tomorrow morning, Tuesday, and then 10 a.m. on Wednesday. That's our town hall. So we're going to bring several industry executives together, and we debate the opportunities and some of the challenges in today's steel industry. We have Dan Brown with us from Big River Steel, Wendell Carter from Cleveland Cliffs. We have Prasanna Joshi representing ExxonMobil. We have Dave Samusky from Nucor, and Chris Graham with Steel Dynamics. So it's an all-star lineup, and we hope to see you there. Again, that's Wednesday at 10 a.m. It's a can't-miss event, and I encourage you to arrive early to get a good seat. As all of our plenary sessions, so this one, and then Tuesday and Wednesday, they will be streamed live, and we hope that this format provides everyone an opportunity to participate no matter where you might be in the world today. And then running today through Wednesday will be the exposition. It's the largest exposition in our history in all aspects. We have 686 companies. That's about 100 more than last year, actually. So there's been tremendous growth in the steel industry and with the AISTech event. We'll have attendee receptions in the hall tonight and tomorrow. They'll begin at 4:30 and run through 6. So Monday night, 4:30 to 6, Tuesday night, 4:30 to 6. We'll have our Chevy Silverado giveaway. It's out there on the floor right now. It's a bright, gray, beautiful truck. I wouldn't mind having it myself, but you got to be present to win that truck. So that'll be at 2:30 p.m. on Wednesday afternoon, and I wish you all good luck with that. Now, before we begin, I would like to point out that you need a blue badge to be in one of our technical sessions, or an orange badge if you're a student. If you don't have the appropriate badging, please do go to the registration counter. It's just down the hall. Also, I'd ask that you mute your cell phones when you're in any of our technical sessions, and please also remember that the recording or the photography of any of our sessions is prohibited. Now, it is my distinct pleasure to introduce this morning's lecturer. The AIST J. Keith Brimacombe Memorial Lecture Award was established in 1999 to honor Dr. Brimacombe's outstanding accomplishments in the area of process metallurgy, his dedication to the steel industry, and his profound influence on the people of our industry. Information regarding now the 25-year legacy of this lecture has been looping on the screen, including the biography for this year's recipient, Dr. Sunday Abraham. Sunday is the Director of Research and Development at SSAB Americas. Time permitting, he will have a question and answer session at the conclusion of his lecture, and we will formally recognize Dr. Abraham tomorrow morning with the President's Award Breakfast. So I hope you can also join us for that recognition. His lecture this morning is entitled Integrated Physics-Based Modeling and Artificial Intelligence for Smart Manufacturing. He's a compassionate leader for AIST. He's a champion for our industry. Please welcome me in joining the 2024 Brimacombe Memorial Lecture, Dr. Sunday Abraham.
Thank you so much. Appreciate it. Good morning. I want to thank Ron for the kind introduction, and I am very privileged to deliver this lecture this morning in memory of Professor Brimacombe. And I appreciate the presence of outstanding individuals that have delivered similar lectures in the past. But before we start, let's watch a short video clip about Professor Brimacombe.
Keith Brimacombe left an indelible impact on the University of British Columbia, the people he mentored, and the industry he studied.
He was, I would say, a visionary, a pioneer, an incredible ability to understand how to connect very disparate pieces of information to provide insight that nobody had actually thought about.
Keith was a little bit unique as a visionary, as he actually looked at the ground we were standing on. He worked with existing industries, he worked with existing technologies, and it was all about improving our understanding of those technologies.
Where some researchers will be happy making a major contribution in one area, Keith Brimacombe was dedicated to researching many ferrous and non-ferrous processes.
The remarkable thing is the areas I worked on with him were two of probably 10 areas that he was working on simultaneously. Just a remarkable intellect and capability.
Many of the improvements and advances made by Keith involved processes key to the mining industry, like his work with zinc fuming and the Pierce-Smith converter. It was his approach to studying these areas that made him unique.
No one in the world had ever done that until he came along and really demonstrated how you could do it most effectively.
Probably his biggest contribution is in the computer modeling of continuous casting processes. And by doing that, he really greatly enhanced our understanding of how that process operates.
Professor Brimacombe possessed a rare combination of intellect, energy, and engaging personality. He was a great scientist, researcher, and innovator whose work had significant impact in academia and industry, and it still does. In my lecture this morning, it is my hope that the examples I will give on the applications of physics-based modeling and artificial intelligence for smart manufacturing are consistent with some of his work that he did. And the industrial revolution started out in the third quarter of the 18th century with the introduction of steam and water power for mechanization of manufacturing. This resulted in agricultural boom, population growth, creation of new cities, and urbanization. By the first quarter of the 20th century, the water and steam power was replaced with electricity, and this resulted in further population growth, mass production of food, clothes, and goods, and innovations in transportation, medicine, and weaponry. And by the third quarter of the 20th century, revolution in computer technology resulted in automation of major industrial processes. In the iron and steel industry, computer technology empowered us to improve the production efficiency and the quality of the product that we make. And now, as the first quarter of the 21st century draws to an end, the availability of massive computing power resources is opening up new landscape for industries to further improve production efficiency and product quality. The history of artificial intelligence started out in the 1940s with the introduction of neural networks for modeling. AI did not gain any popularity until in the 80s and 90s when successful cases of its applications were reported, including a computer program called Deep Blue that beat the world chess champion. Then in 2009, the first self-driving car was created. And then in 2011 through 2014, a few personal assistants such as Siri, Google Now, Cortana, Alexa were created. And now artificial intelligence is opening up a new frontier of research for rapid innovations in different industries. In the steel industry, the safety and health of our employees have always been at the forefront of our operation. And now with the availability of AI and robotics, we are further enhancing this opportunity to ensure that we don't put employees in harm's way. But let's watch a short video clip about the early state of concern of safety.
Many of the men at Homestead work 7-day weeks, holding down 12-hour shifts. Every 2 weeks, they'd do a turn, working 24 hours straight. The majority earn less than $2.50 a day.
This was a place where the furnaces were working 24 hours a day. The sky would be lit up by the light of the furnaces. Pittsburgh in the 19th century was compared to hell more often than any other city because of how dark and obscure the sky was.
And walking into a steel mill in that era would have been a staggering experience. It was like walking into the jaws of hell itself. You had these vast furnaces, superheated molten metal being poured, splattering. It was like the 4th of July. Molten metal flying everywhere. It was majestic, it was awe-inspiring, and also very dangerous at the same time. And also tremendously difficult work. People talked about sweating so much that their shoes would be squishing full of water from their own perspiration, that inside of an hour on the line, it would be as if they were walking through a swamp.
And today, it is very common to see robots being used to measure the temperature of liquid steel, robots being used to take samples for chemical analysis, and robots being used to repair the refractory in furnaces, and robots being used to mark IDs on NASCAR's product. And some are beginning to use robots for housekeeping. With AI, digital evolution, and computer technology, it is no longer necessary to install glass windows in the pulpits of operators. It is actually important to locate the pulpit far away from the electrical furnaces to make sure that employees are not in danger. So, but there are opportunities where physics-based models and AI can be combined to optimize processes, improve quality, and product performance. The examples I will give is based on electric arc furnace route of steelmaking. The electric arc furnace steelmaking process is an energy-intensive process. 65% of the energy required to make scrap comes from electricity, and the remainder come from various chemical reactions. The temperature of the arc ranges from 2,800 degrees C to 19,000 degrees C. As a comparison, the temperature of the surface of the sun is only 5,500 degrees C. The sound of the arc as it melts down the scrap is akin to that of a thunderstorm. The process is multiphysics, involving chemical reactions that are in different phases that are in thermodynamic pseudo-equilibrium with each other. All of this creates an environment that is harsh, aggressive, and corrosive. Hence, it is impossible to continuously measure the temperature of the bath during the scrap melting. A decision on when to make intermittent temperature measurement is based on the judgment and the experience of the operators. Hence, this can lead to inefficiency in the process. So because of that, as a solution, we decided to develop an energy and material balance model to help the operators understand the state of scrap melting in the furnace. The energy inputs and outputs were systematically identified and quantified, resulting in a complex equation for predicting the temperature of the bath during scrap melting. So the red curves that you are seeing here, they are the predicted temperature of the bath during scrap melting. As you can see, they are in good agreement with the measured temperatures that are represented by the open circles. In our model, we incorporated a sub-model for oxidation kinetics to predict the chemistry of the bath during the scrap melting. So our model can predict carbon, aluminum, silicon, and manganese content of the bath. So as a result, we have a comprehensive model that provides guidelines to the operators on the state of scrap melting in the furnace. So optimal slag chemistry and good slag forming is very important for the efficient operation of the electric arc furnace. If the slag doesn't form well, the arc is exposed, and the roof and the wall of the furnace can be damaged from the intense heat radiation from the arc. Now, if the arc does form well, let's see here, then the slag completely engulfs the arc, maximizing heat transfer onto the scrap. And also, this process minimizes nitrogen dissolution from the air into the steel, which is good for the quality of the steel. But operators do not know exactly what the chemical composition of the slag is during the scrap melting. So to provide a solution to this, we decided to develop a model for predicting slag chemistry. So by studying the historical data on slag composition and steel chemistry, we determined that the capacity of the slag to absorb phosphorus from the steel is highest when its concentration is in the optimal range. So using mass balance analysis of the fluxes that were added to the electric arc furnace during scrap making, melting, and in cooperation with our sub-model on oxidation kinetics, we developed a slag model to predict the slag chemistry. The green curve represents the predicted slag chemistry, and the red curve represents the measured slag chemistry. As you can see, there is very good agreement between the predicted and the measured slag chemistry. Now, operators can use the model then as a reference to adjust the slag chemistry as appropriate. After melting, the steel is tapped from the furnace into the ladle for subsequent processing. During tapping, it is very important to minimize slag carryover from the electric arc furnace into the ladle. It is equally important to ensure that you have adequate heat in the furnace for subsequent scrap melting. There are two ways of doing this. One is the use of load cells to measure the weight of the steel in the ladle and in the EAF during tapping. Needless to say, this is a precise technique. But under the harsh environment of electric arc steel melting process, load cells frequently break down. Hence, they are maintenance intensive and costly. The second method is using the slag detection system coupled with eyeballing of the level of the steel in the ladle. This method is not precise. It doesn't give you exact weight of steel in the ladle or in the electric arc furnace. Hence, the heel can quickly run out of control as shown on this chart. So inconsistent heat in the furnace can lead to overcharging of scrap in the electrical furnace, undertapping of liquid steel into the ladle, EAF overload, poor scrap inventory management, and poor yield. As a solution, we decided to develop a model to predict tap weight and heat in the electrical furnace. So our approach is actually to measure the change in ladle volume during its campaign. The ladle does change its volume during this campaign because the refractory wears out with time. So by looking at historical data on refractory tear out, we developed a mechanism for measuring the profile of refractory wear in the ladle. Hence, we're able to calculate the ladle volume at any given time. So when a ladle is designated for tapping and a tap weight is specified, our model determines the freeboard in the ladle. And then you can now use a thermal imager to monitor the temperature of the refractory in the freeboard region. And then as the level of the steel is rising and when it contacts the freeboard region, the change in temperature can be used to terminate tapping, leading to consistent heat control during scrap melting in the furnace. So now, after tapping, the ladle is sent to the ladle metallurgy station for refining. Refining is the most intense of all steelmaking process steps. The reason is that the operators have to perform multiple tasks within a very short period of time. The operators have to ensure that they add adequate amount of deoxidizers and fluxes for efficient desulfurization and deoxidation. They have to ensure periodic and addition of multiple alloys into the ladle as they sample the steel to test the chemistry to ensure that the chemistry is within the specification that is required for that particular grade. They have to provide adequate heating to the bath to make sure that the ladle is sent to the caster at the required temperature. They have to ensure good argon stirring in the ladle to ensure that we have chemical and thermal homogeneity. And they also have to ensure that in that process, they enhance inclusion removal before the ladle is sent to the caster. But slag engineering is very key to the quality of the steel at the end of the refining process. An engineered slag has to have high sulfide capacity, low interfacial tension, and good fluidity. All of these properties depends on the composition of the slag. Unlike the steel, it is operationally inefficient to sample the slag for chemical analysis during the refining of steel in the ladle. But fortunately, the slag does change color as its composition changes. And operators rely on this change in color to determine whether they have a good slag or not. But this doesn't always work the way we want it to be. What we're showing here on the chart is evolution of sulfur during refining of the steel at the ladle metallurgy station. For the first 60 minutes of refining, the sulfur removal rate was very low. The operators had to rake off the original slag, make new slag, before they had rapid desulfurization in that particular heat. But as you can see, that heat took us almost 200 minutes to process at the ladle metallurgy station, compared to typical 30 to 45 minutes of refining. So needless to say, this resulted in operational delays and productivity loss. So as a solution, we decided to develop a model to predict slag chemistry during refining in the ladle. For a model to work, we have to identify and quantify oxides from different sources that make up the slag. For example, the EAF slag carryover was calculated based on the phosphorus change from tap chemistry to the first LMF test. The alumina that is formed is calculated based on the oxygen potential of the liquid steel and the oxygen from the air that is entrained. Then we also consider the amount of fluxes and the chemistry of fluxes that were added during refining in the ladle. Then we look at historical data between the slag composition and the steel to understand how the slag composition affect sulfur removal. With that data, we're able to group the slag into various categories. We have fluid slag, high sulfide capacity, semi-crusted slag, low sulfide capacity, semi-gummy slag, low sulfide capacity, and so on. And by normalizing the concentration of the slags, we are able to represent them in the ternary plot of calcium oxide, MgO, and alumina. So the operators can see the condition of their slag during refining in the ladle. Now, what you are seeing on the right here, you can see the predicted slag condition is that of the heat that I reported on the previous slide that experienced difficulty desulfurizing. Our model was able to determine that the slag is semi-crusty and has low sulfide capacity. What is also neat about this model is that it is able to recommend what materials to add to the flux, to the slag, to change it to favorable slag condition. In this particular case, the model is recommending that some aluminum and some high-Ca lime should be added to make sure that the slag condition is changed to a favorable conditions. Hence, operators can rely on this model to adjust the slag condition during refining in the ladle. So one of the tasks that the operators have to perform during refining at the ladle metallurgy station is to ensure that we reduce the population densities of non-metallic inclusions before they send the ladle to the caster for casting. Non-metallic inclusions can be very detrimental to the mechanical properties of steel because of the disparity between elastic and thermal properties of steel and non-metallic inclusions. So properties such as resistant to fatigue, toughness, resistant to hydrogen-induced cracking can be degraded because of the presence of significant amount of inclusions in the steel. But fortunately, solid non-metallic inclusions tends to float up into the slag steel interface where they get absorbed by the slag. So this behavior is described by the Navier-Stokes equation, which shows that the upward velocity of solid non-metallic inclusions is directly proportional to the square of the radius. So if you take two alumina inclusions, one that is 100 micron in diameter, and the other one that is 10 micron in diameter, the 100 micron in diameter will float upward into the steel slag interface in less than 4 minutes. The 10 micron inclusion will float up into the slag metal interface in about 400 minutes. So, but the 10 micron inclusions can be very detrimental to the mechanical properties if they are present in large population. But we don't have 275 minutes to waste. Otherwise, we will not be in the business of steel making. So as a result, but some other researchers have done work and show that argon bubbling can enhance flotation of non-metallic inclusions during ladle refining. The reason for that is that the size of the argon bubble is significantly larger than the size of non-metallic inclusions. And also, the bubbles, the argon bubbles, are significantly lighter than non-metallic inclusions. So the upward velocity is very high. So if inclusions get attached to those bubbles, that will enhance their flotation from the liquid into the slag metal interface. But we decided to investigate this phenomenon further by doing experiments. In one of our experiments, we allowed two ladles to idle for some times after the steel has been killed. The one ladle was idle for 97 minutes with no alloy addition and no argon stirring. And the second ladle was idle for 57 minutes, but with 10 SEFM argon stirring. We sampled the steel before the idle time and after the idle time for non-metallic inclusions. And what we found is that the ladle that was idle for 97 minutes with no argon stirring has significant decreases in the population densities of non-metallic inclusions. whereas the ladle that was idle for 57 minutes and stirred for 10 SEFM with argon has significant increases in its inclusion population density. So we concluded that the argon stirring probably perturbed the flotation of non-metallic inclusion from the steel. Now we are in a movie, right? I can't see anybody. And then in our second experiment, we had a ladle of steel, and we sampled the steel from the beginning of refining to the end of refining. And we found out that the refining process can be divided into two regions, or two stages. Stage one is where we had very rapid decline in the population densities of non-metallic inclusions. And stage two, where we have significant increases and gradual increases in non-metallic inclusions. We also found that the inclusions in stage one were significantly larger in size compared to the inclusions in stage two. So what we concluded is that, in the first stage, when we have high oxygen potential and the slag is not fluid, we form very large inclusions that quickly flowed up into the slag steel interface where they get absorbed by the slag. Then in the second stage, the slag is now fluid. The oxygen potential is very low. We form small inclusions. Small inclusions are perturbed by the argon stirring. They can float up quickly. And then not only that, because the slag is fluid, if you are stirring aggressively, you entrain slag particles back into the steel. So what we found is that, in stage two, the population density of slag particles that is entrained back into the steel is directly proportional to the argon stirring rate. So, but overall, we found that, in aluminum keel steel, pure alumina is not the predominant inclusions in the steel. Most of the alumina is tied up as calcium aluminate, magnesium alumina, and complex oxide. However, we found that, with increasing aluminum in the steel, the oxygen potential tends to decline. So using this relationship, we can actually calculate, how much calcium is required. You remember that 10 micron size inclusions that doesn't float out, quickly. Well, so we can determine how much calcium to add to modify those inclusions, the residual inclusions, to make sure that they don't result in operational problem or cause, negative impact on the mechanical properties. But if we also know the sulfur content of the steel, we can calculate, how much calcium is required to completely modify the oxide and the sulfide inclusion. So we have a calculator that, at the end of refining process, we can determine for any calcium-bearing agent how much of that material should be added to ensure that the sulfide and the alumina inclusions are effectively or efficiently modified. So, and what we found is that, the modification efficiency, I'm too fast here. The modification efficiency of sulfides is related to the calcium to sulfur ratio, and the modification efficiency of alumina inclusions is related to calcium to oxygen ratio. We also found that if the sulfur content is higher than 30 ppm, it is impossible to completely modify the sulfide inclusions. So at the end of refining, the ladle, once refining is complete, the ladle is sent to the caster for casting. At the caster, the steel flows from the ladle into the tundish and then into the mold where it begins to solidify. As the strand solidifies, it is gradually withdrawn away from the mold. The withdrawal speed of the strand should be consistent with the flow of liquid steel from the ladle into the tundish and from the tundish into the mold. But there are two incidents that can interfere with this flow dynamic. And one is in the tundish, the stopper rod that is used to control the flow from the tundish into the mold, you can have severe erosion at the tip, leading to uncontrolled flow from the tundish into the mold. And the SEN that distributes the flow in a certain pattern in the mold can be clogged, choking off the flow from the tundish into the mold. By looking at the historical data, we found that these two events are related to the calcium content after calcium treatment in the ladle, and also to the amount of fading, calcium fading that occur during continuous casting. I.e., if the calcium content resides to the right of the green zone, there is high potential for stopper rod erosion. And if the calcium content is to the left of the green zone, then there is high potential for SEN clogging. We identified other process variables that can affect stopper rod erosion or SEN clogging. And then we decided to use a cluster analysis algorithm, a type of machine learning algorithm, to predict the stopper rod behavior. So based on historical data, each process variable is classified into clusters with tight boundary conditions. So this allows us to identify a combination of process variables, and there's light again, a combination of process variables that will lead to either stopper rod erosion or SEN clogging. For example, if you take a heat that ended up with 10 ppm calcium, calcium to sulfur ratio of about 3, an aluminum addition before calcium treatment of about 100 pounds, an aluminum addition after calcium treatment of about 100 pounds, and then with argon rinse time of about 2 minutes. This combination of process variable will lead to neutral position, i.e. no stopper rod erosion, no SEN clogging. When you compare it to another heat that ended up with a calcium of greater than 15 ppm and calcium to sulfur ratio of about 4, aluminum addition before calcium treatment of 150 pounds, argon rinse time of about 3 to 5 minutes, aluminum addition after calcium treatment of about 100 pounds, and argon rinse time of about 1 minute. This combination of process variables will lead to severe stopper rod erosion. What is also good about this model is that the model can make recommendations to the operators on what to do to prevent either of these conditions, stopper rod erosion and SEN clogging, from happening. So temperature of the liquid steel during casting is very important to the operational efficiency of casting and to the surface and internal quality of the as-cast product. Temperature is measured in the tundish either with a continuous temperature measurement sensor or intermittently with a temperature probe. Continuous temperature measurement sensor, you learned this already, is maintenance intensive and costly. Intermittent temperature measurement is not good for process optimization and control. So hence, we decided to develop a model to predict temperature in the tundish. The model is based on fluid flow and thermal balance analysis. So the red curve that you are seeing here is the predicted temperature, and the solid circles are the measured temperature. You can see that there's very good agreement between the measured and the predicted temperatures. So what is neat about this model is that for all slabs that are cast in the sequence, we can map out the superheat of all the slabs and then correlate that to the surface and internal quality, and also use that to optimize shipping temperature from the LMF to the caster. So of everything that can happen during the continuous casting, none is more devastating than strand breakouts. There are many reasons why strand breakouts occur, but the one I want to focus on is the hydrogen-nitrogen-related strand breakout. So during solidification, the solubility of hydrogen and nitrogen decreases. So as the shell is solidifying in the mold, we have molecules of hydrogen and nitrogen that are coming out of the shell. And they can be trapped in between the shell and the mold wall, decreasing the heat transfer from the shell onto the mold wall. So at the exit of the mold, the shell can be so thin that it cannot withstand the ferrostatic pressure of the liquid inside it. So this creates potential for breakout. So by looking at historical data on hydrogen-related breakouts, we found that with every 1 ppm increase in hydrogen, you have to decrease the nitrogen by 20 ppm to avoid the potential for breakout. We also understood the relationship between the hydrogen and nitrogen content of the steel and heat transfer during casting. Using all of this information, we developed a model to warn the caster operators of when a hydrogen-nitrogen breakout is imminent. So what you're seeing here, where the model indicated to the operator that they should stop casting, they didn't stop casting on time, and hence they did have breakout on that heat. But I should say, if you have a degasser like my company does, you don't have to worry, and you use it effectively to remove hydrogen, of course, and nitrogen. You don't have to worry about strand breakout during casting. So the as-cast product is referred to as semi-finished product, and it is not good for most applications. The reason is that the chemistry and the microstructure is not homogeneous throughout the thickness, and it is not uncommon to see defects such as centerline segregation, shrinkage cavities, and pores and voids in the center. The chemistry can be homogenized through reheating in the reheat furnace, and the microstructure can be refined, and the centerline defects can be healed through thermomechanical deformation. During thermomechanical deformation, many microscopic phenomena such as precipitation, phase transformation, recrystallization, recovery, dislocation, and etc. occur. These microscopic phenomena, they interact in a complex manner with each other and with macroscopic factors such as chemistry, temperature change, strain rate, number of passes, interpass time, etc., to influence the finer microstructure and mechanical properties of steel. We can rely on CCT diagram or TTT diagram to predict the microstructure and maybe some properties of certain steel grades. But developing physics-based model that can precisely determine microstructure and mechanical properties is very difficult because of the complex synergistic effects that the microscopic phenomena have with each other and with the microscopic factors. But nevertheless, Hodgson and Gibbs developed physics-based model for predicting the microstructure and mechanical properties of carbon manganese hot rolled steel. In their model, they considered microscopic phenomena along with their synergistic effect, but with huge assumptions. Their model is intended to predict microstructure and mechanical properties for carbon manganese steel where ferrite is the predominant microstructure. So hence, accurate determination of ferrite grain size is very important to the performance of the model. So when they apply their model to predict the yield strength for different carbon manganese steel, they found that the prediction is pretty accurate for ordinary carbon manganese steel. Now, when they use the model to predict for carbon manganese steel that has multiple microalloying elements, the accuracy declines significantly. In the 80s and 90s, there was significant effort undertaken to develop artificial neural network models to predict microstructure and mechanical properties. Artificial neural network models are more accurate and have wider application compared to the physics-based models. However, the problem with artificial neural network models is that as soon as they are applied on data set outside their training set, the accuracy declines significantly. So in the steel industry, our approach to product development is actually to rely on the basic knowledge of metallurgy and the experience of the metallurgist. The metallurgists design new products, and they adjust the chemistry and process parameters for all products to make sure that their mechanical properties meet the intended properties. But this is based on trial and error. It is time consuming, and it can generate significant waste. The charts that I'm going to show in a second is showing the relationship between the yield strength and thickness of two grades of steel. On the left is a grade requiring 36,000 psi minimum yield strength. You can see that all of the products there meets this requirement. But if you look at the lighter gauges, they are about 10,000 psi higher than the heavier gauges. Now, on the right is a grade of steel requiring a yield strength minimum of about 65,000 psi. You can see that when you go to heavier gauges, you begin to see products with yield strength that is below the required minimum of 65,000 psi. So a potential solution to minimizing such waste with respect to product development is to maybe apply cluster analysis algorithm for products development. For these particular kind of cluster models, we can identify measurable and known process variables that impact microstructure and mechanical properties. And then based on historical data, classify each process variable into clusters with tight boundary conditions. Each grade, each chemistry type will have its own cluster model. This way, we can identify a combination of process variables that will lead to certain mechanical properties. Such a model can be applied online for troubleshooting and prediction of microstructure. It can be used offline for design of new products. Now, before I end my lecture, I would like to talk about the potential or the perceived danger that AI poses to our society. I think you all remember this. In November of 2022, when ChatGPT was launched, it created a significant hype in the society. Everybody was worried that AI is going to take their job away. And if you listen to the concern that people have, you will think aliens have finally landed on our planet. And our existence as you know it is about to end. But in her article, Alison Whiting, the article entitled Me, Myself, and AI, she said that AI will not replace professionals like doctors, lawyers, and journalists. My daughter is a lawyer, so I support you. They will not replace you, but I add, and I'll add, I say yes, engineers and politicians too. And then she went on to say, those who work with AI will replace those who don't. But essentially what Alison is saying is that AI will not replace us or make us extinct, but it will change the ways we do things. The benefits include better employee safety, health, improved efficiency and productivity, and accelerated decision making. So how about baby robots? They are cute, and they do amazing things as well, and many people are fascinated with them. But, baby robots will not replace our pet. They are not as cuddly, so they don't have mind of their own. In conclusions, application of physics-based modeling and artificial intelligence to our processes can improve the bottom line of our business by helping us discover new relationship between process parameters and product performance, optimize production processes and realize cost savings, improve product quality performance and minimize waste, enhance our technical know-how, predict product properties while products are still being made, reduce the time it takes to design new products, make decisions rapidly. For example, decisions on product application can be made as soon as loading is complete. There are many, many people that contributed to the lecture I delivered this morning. I would like to acknowledge those people. Ian Dix, a former employee of Nucor who has now retired, Chad Cathcart of Stakehold, and April Badgett of Nucor. Yufeng Wan, who worked with me to develop some of the models presented here today. Xiaojie Chen, who worked with me at the former IPSCO. And then various co-ops and interns from different universities. SSAB senior management team, Ben Cohen, Tom Turner, Chuck Schmidt, thank you for your support and your vision for our company. Lee Hendon, SSAB America's Communication Director, all other SSAB employees who are here today or are watching online, and my family, my wife, Elena, thank you for your unconditional support and what you've done for our family. And my daughters, Victoria and Jane, I'm very proud of you. And Chris was unable to make it. I thank him anyway. And my brothers, Abraham and Meza, I am grateful to our mom for instilling the value of education in us. And you know, my nephew, Isaac, thank you for coming. I want to say that AIST has a place for people as young as you, too, so you know. And of course, Ron Ashburn and all the entire staff of AIST, thank you for the opportunity. Thank you. Thank you.
We do have a few minutes for any questions for Dr. Abraham. We have a microphone, we'll come to you. Please tell us who you are and your company, please.
So, Dieter Betting, I'm from Brimacombe Technologies.
Okay.
Many thanks for the interesting presentation. And I think you pointed out the strength if you combine classical physical modeling with AI. My question is, you also mentioned that AI models are good when interpolating, so making predictions or statements about things where there was some past experience from training data. And they have a big problem with extrapolating.
Correct.
And as they are black box models, or tend to be black box models, they do not show that typically. How do you handle that?
Black box models?
All neural network models, they typically don't show when they will break down and in practical operation. So how do you handle that?
Well, you know, the point is that when you have a black box model, they tend to have very complex equations, and they cannot be applied online for prediction of properties or any particular process variable that you're looking for. To break it down, you have to ensure that you have wider historical data to tune that model to, and then limit it to that application alone. Because when you do apply it outside of the data, the training data set, you're not gonna get accurate prediction. I hope I answered your question.
Yeah, in some areas that might be challenging, like if I understand if you have a closed status space, so where similar things happen all the time. But it's like if you want to use it for control of a blast furnace, then it could be quite demanding, right?
It is quite, again, you know, you have to, for AI models, you can apply it widely to everything, you know, unless they are trained on that data. You know, once you start feeding out into other data into it that are not trained for, then the prediction is not that accurate. Yes.
Hello, this is Jeff Brooks from Swinburne University. Sunday. Hello.
Oh, okay. Well, I'm looking at wrong. Okay.
Yes, go ahead, sorry. Yeah, I'm Jeff Brooks from Swinburne University. Congratulations, Sunday, on a great talk. Really excellent talk. You outlined very well the use of models to predict things like the dynamic heat and such things.
Mm-hmm.
But I'm a bit worried that we are still a little bit addicted to recipe-based feeding systems into our furnaces.
Yeah.
So we're not taking advantage of it. So I'd like to get your views. For example, perhaps we should be thinking a lot more about semi-continuous feeding into furnaces so we could match the heat load and the generation of energy. Do you think that's correct, or what do you think? Are we fully utilizing these models to the biggest advantage?
Yeah, the one thing is that when you're talking about the electrical furnace on its own, there are so many variables that can impact any models that you have, whether physics-based or artificial neural network models. The reason, for example, if the scrap doesn't have optimal quality, let's say you have the scrap and you have a lot of non-metallics in your scrap, which you don't know, that can impact the prediction of your model, whether it is physics-based or artificial neural networks model. So I think over time, once you understand, for example, you have the EF model, once you understand your scrap recipe, you can tailor each particular model to that scrap recipe to make sure that you always get the optimal performance from the model. You're welcome.
Okay, it's working. Jeremy Jones, CIX.
Yes.
So Sunday, two questions. The first one is related to having to have a sound fundamental basis for any model.
Mm-hmm.
And at times I see AI being applied where it will pull in things. I'll give you an example. So there was an assessment on breakouts in a caster, and for some reason, one of the variables that was included was the day of the week, and it was found that on Tuesdays, you're much more likely to have breakouts because that's what the historical data showed.
Yeah.
Of course, if you go back to the fundamentals, you say, look, it doesn't make sense. It's just like statistics. You can always find, and the more variables you use, the less degrees of freedom, so you always get a perfect fit.
Yes.
So that's the first part, and then I have a second part on safety. So why don't you go ahead and respond to this one?
That's a very good point. That is the downfall of artificial neural networks model. And that's why they call them black box models, because what you put in is what you get. And sometimes in the equation, if you have to look at the equation, it doesn't make sense. And they tend to, really highlight the noise levels, So in your example, the breakout, it says that the day of the week affect the breakout. Yeah. That doesn't make sense. But if you also think about it, if it is in the winter season, that doesn't make sense. If it is when it is humid and you have hydrogen in the steel, maybe that makes sense. But you can't quantify the day of the week. What we can quantify is humidity. So if you can quantify that, then that makes sense to incorporate that into the model.
Yeah. So what I'm trying to do is justify the fact that we can't get rid of engineers because you need someone to vet the model. So it's just self-justification. I only have 3 or 4 more years. So I'm probably good. The second question is, so we've seen this huge move in the industry towards no man on the floor, safety, and so forth.
Sure.
What we're trying to do now is replace the functionality of humans with machinery and models and so forth. But what I see is that sometimes there's a lack of recognizing what a human sees when he looks inside a furnace and checks things, and what a system can do. So do you think that there's also a need to continue to really expand? When you replace a human with equipment, you need a higher level of instrumentation, you need a higher level of sensory perception, because people underestimate how much a human sees compared to a machine.
I agree with that. I think, if you look at it, we're never gonna get rid of experienced people on the floor because the robots, the sensors, again, they do break down, right? So we need people that understand the process itself to oversee it. And sometimes, what you get from them may not be correct. So yes, it's a human-robot AI interaction. It's not one for the other, So that's what I would say.
Yeah, no, there's a synergy. I agree completely.
Okay.
One more question. Ron, did you have a question?
Yeah. So, Ron O'Malley, Missouri S&T.
I know you.
Great talk. I'm sorry. Hey,
Thank you.
I'm really curious. What software tools are you using to do the neural network within your company?
You know, the software that we're using, I'm not a software engineer, I can't tell you. And if I tell you, I have to kill you also. So, anyway.
So how many beers?
So.
All right, we're going to have to wrap it up. I'm sure Dr. Abraham will be available after the session to answer any other questions you have. We will again formally recognize Sunday tomorrow morning at 8 a.m. with the President's Award Breakfast. Dr. Abraham, on behalf of the AIST community, congratulations on being our Brimacombe Memorial Lecture. This concludes our opening technical session, 474 more to go. Please have a great experience with AISTech this year. Thank you all.
Thank you. Thank you, sir. Appreciate it. Thanks.
Great job, Sunday.
Thank you. Appreciate it, Ben. Thank you. Appreciate it.
Congratulations.
Thank you.
Nice to see you.
Appreciate it.